Mm-hmm. Yeah.
All right, for the second talk of the morning session, we have David Meretzky for University of Notre Dame going to Universidad de los Andes. He's going to speak on differential Galois theory with new algebraic constants.
Thanks. Thanks, Omar. And thanks so much to the organizers for the invitation. It's really nice to be back here. This project was started at Fields in 2021 during the model theory thematic semester. And so it's good to be back here and talking about it. This is chapter 4 of my recent thesis under Anand's supervision. So just to give a little overview, in 1948, Colchin gave the first fully algebraic account of the Picard-Vessiaux flavor of differential Galois theory. And a few years later, a student of his at Columbia, Marvin Epstein, who was working on existence theorems for Picard-Vessiaux extensions, gave an existence result for a slightly broader class of extensions where the no new constants requirement is dropped. And he studied a kind of partial Galois correspondence for this broader class of extensions. So the goal of this talk is to give a model theoretic treatment of Epstein's work. That's what I'm presenting, although the statements will be differential algebraic, at least in the first part of the talk. And towards the end, I'll give kind of a more intense model theoretic description. So sorry to the dynamicists. And kind of one of the reasons to give a model theoretic treatment is to possibly generalize Epstein's work to broader classes of extensions beyond the PV case. And I'll also state some precise relationships with a notion of differential extension introduced by Umemura in about 1996 called quasi-automorphic extensions. Okay. All right. So as we saw in Dave and Christine's talks have introduced a lot of the fundamental notions, so I'll go through this pretty quickly. So a differential field again is, a field K together with an additive map, which also satisfies the usual product rule from calculus. And in this talk, we're going to focus on the ordinary one derivation case in characteristic 0. So just basically to set notation, the theory of differentially closed fields of characteristic 0 in the language of rings together with a symbol for the derivation has a model companion DCF0, the theory of existentially closed difference fields. And it's a nice theory. It has quantifier elimination. It has elimination of imaginaries, which means if you take a definable set and you have a definable equivalence relation and you quotient by that definable equivalence relation, you remain, you get a definable set again. And it's totally transcendental, which is kind of a generalization of the condition of omega stability, which we saw earlier, but potentially working over uncountable sets of parameters. Yeah, yes, DCF0 with no parameters is, yeah, in general, yeah, okay, fine. Okay, fine. Yeah, okay. Yeah. Okay. Okay, every differential field has a subfield of constants. So for example, Q adjoint T with DDT, the field of constants are just the rational numbers. So as DCF0 is omega stable, so every differential field K of characteristic 0 is contained in a prime model of the theory, which I'll write as K diff, which is equivalently the differential closure in differential algebraic terminology. So we saw this fact in Dave Marker's talk that the differential closure is an atomic model. And we also saw, so as a consequence, the constants, if I take a differential field K and I take a differential closure, the constants of the differential closure containing K are the algebraic closure of the constants of the base field. We saw this in the hypothesis of that theorem by Rosenlicht. So I'll give a terse review of the Picard-Vessio theory. So given a differential field K, an ordinary homogeneous linear differential equation is an equation of this shape. So it's linear in y and its derivatives with coefficients in K. And a kind of basic fact, which one proves by this Wronskian lemma from an ODE class, is that if you take any differential field extension L of K, you take any ordinary homogeneous linear differential equation y over K, and you look at the solution set in L in this extension, this is a CL vector space, so vector space over the constants of L of dimension at most the order of the original equation, this n that's appearing in this equation. A fundamental system of solutions to this equation is then a CL basis in some extension of the vector space of solutions, which is of the maximal length. So it's of it attains this it's of length n, where n is the order of the equation. Okay, so in particular, if you take an arbitrary differential extension, it may not actually contain a fundamental system because you may not have enough, CL linearly independent solutions. Okay, a Picard-Vessio extension, K contained in L, is a differential extension generated by a fundamental system of solutions as a differential field to some ordinary homogeneous linear differential equation over K, such that no new constants are introduced. So CL equals CK. And so in this case, the solution set is going to be actually it'll be a CK vector space of dimension n. Okay, so a kind of basic example where we're not assuming the constants of the ground field to be algebraically closed is the following. So you treat Q as a differential field where the derivation treats everything as trivial, and that'll be K, so it's a constant differential field. Q adjoin e to the t is a Picard-Vessio extension for the equation y prime minus y equals 0. And so E of t is a Q basis of this thing. Okay. So let me give the first existence theorem, which appears in this Colchin school for Picard-Vessio theory. So given a differential field and y, an ordinary homogeneous linear differential equation over K, this is a fact from a paper of Colchin. Colchin published 2 papers in 1948, which I'll refer to as 48A and B. So in 48A, he proves the following well-known criterion for existence, which is that if the constants of the base differential field are algebraically closed, then there's a Picard-Vessio extension L, which can be found intermediate between K and differential closure of K, fixed copy of the differential closure of K. So because K-diff, this is kind of the model theoretic proof, because K-diff is an existentially closed differential field, one can find n independent solutions, B bar, so find a fundamental system in K-diff, and then just generate the field, just generate L by this as a differential field by these n independent solutions. And then because of this fact that the constants of the differential closure are the algebraic closure of the constants of the base field, it'll just be the case then for any intermediate L between K and K-diff that this extension has no new constants. Okay. So this illustrates the kind of phenomenon, the following phenomenon, that existence and uniqueness / multiplicity of Picard-Vessio extensions is sensitive to field arithmetic, model theoretic, and Galois-cohomological properties of the field of constants. So in this case, it's sensitive to the very, first field arithmetic property of just being algebraically closed. Okay, so now I will kind of put up the the fundamental theorem for Picard-Vestio theory, and kind of state the correspondence, but I'm going to draw a better picture. Okay, so let L over K be a Picard-Vestio extension, and we're not going to assume that the field of constants is algebraically closed. Then there's a linear algebraic group defined over CK, so that firstly, the differential field automorphisms of L over K are isomorphic as an abstract group to the CK points of this algebraic group. Okay, and there's an associated correspondence, which I'll call the lower direct Galois correspondence, between intermediate differential fields between K and L and CK points of CK definable algebraic subgroups of G. And this associated correspondence is partial. It is not a full correspondence. So in particular, the map which goes from intermediate differential fields to groups of this form is not injective. Okay. Just the trivial the trivial group, just the identity. I don't know. I picked some notation there. Okay. All right. Secondly, if we look at the CK diff points, equivalently the points in the algebraic closure of CK, this group is isomorphic to the automorphism group of the extension where we adjoin the constant CK diff. And here, okay, and how does this map work? Well, in both cases, the map essentially works as follows. 1 and 2, it works by you take an automorphism, you apply it to this fundamental system, to this basis, you get a different basis, and essentially it's just giving you the matrix which multiplication on the right goes from one basis to the other. Okay. There's a correspondence between intermediate fields between this upper extension and algebraic subgroups of G, which I'll call the upper direct correspondence. I'll draw it over there in a second. And that's a full correspondence. And then there's an indirect correspondence, which I will draw also in a second, which is full. And this is what people usually refer to as the Galois correspondence in this setting, is this indirect Galois correspondence. Okay. Okay. So we have the following. So here we have intermediate fields. Oh, sure. Thank you. So intermediate differential fields, K is contained in L1 is contained in L. Okay. And this goes by fixed fields, or sorry, stabilizer and fixed field to the set of CK points of CK definable algebraic subgroups of G, of this group G. So again, right, trivial subgroup G1 CK intermediate in the CK points here. This is not a full correspondence. Now, what we can do here is we can adjoin CK diff. So I hope this is big enough. And here we have intersect with L going down. And here we have intermediate fields. Okay. K adjoin CK diff. Oh. It's contained in, I'll call this L1 tilde. I'm sorry for the notation there, but that's what I have going. CK diff. Okay, and this corresponds directly again by stabilizer and fixed field or stabilizer and stabilizer, I guess, in both directions. So it's really CK diff points. I'm identifying with the CK diff points, which is an algebraically closed field of CK definable subgroups of G, the Galois group G. So we have intermediate E, say G1, or yeah, I should write it as G. I guess I'll just write it as G1 contained in G. Okay, and I'm going to identify G with its CK diff points, which again is algebraically closed. CK diff points. Okay. All right. So this is what I'll call the lower direct correspondence. It is not a full correspondence. This upper correspondence is a full correspondence, and this is a full correspondence. Every intermediate, the set of intermediate fields here is in bijection with the set of intermediate fields here via this adjoining CK diff and intersecting with L, and it's a full correspondence. So composing these two full correspondences is what is referred to as the indirect Galois correspondence. It's a full correspondence. Okay. All right. Let me give now an instructive example that we can see what's happening. Okay, so this is kind of the same example that we saw before. So we're going to look at Q as a constant differential field and Q adjoin. Okay, tell me if I'm writing too small. Q adjoin e to the x. Okay, so the intermediate differential fields here, for example, are Q adjoin e to the 2x, or for any appropriate n, e to the 3x, for example. Oh, thank you for changing the lights. Over here as a subfield, we have Q adjoin e to the 4x, and so on and so forth. So on and so forth. Here we have, right, Q adjoin e to the 6x as a subfield, etc., etc. Okay, and it keeps going. Okay, so this is infinitely many intermediate differential fields. Okay, in this case, the Galois group is going to be the multiplicative group, and so over here, what are the subgroups of what are the the Q definable algebraic subgroups of the multiplicative group of Q? There's actually only one, which is -1 and 1. Okay, there's nothing else here. Okay, so we sort of have a problem. Okay, but if we go up to Q adjoin, or sorry, Q alg, and we look at Q alg adjoin e to the x. So if we adjoin, so if we now have some, so again, the lattice of intermediate differential fields is exactly the same. Q adjoin e to the 2x, Q adjoin e to the 3x, etc. Again, there's infinitely many, and they're actually still in bijection here. But Q alg, thank you. Sorry. That's the important bit, even. Thank you. Okay. So over here, we actually get a full correspondence. What were we missing? We were missing the other roots of unity. So here's mu3, etc. Okay. So we get, and here's -1i what is this? 1i -1 -i, for example. Okay. So we have a full correspondence here. Okay. So again, we have maps going up and down. We have some maps going this way. And okay. So I'll introduce a little bit of notation here. So the set of intermediate fields. Okay, so for example, right, like Q Q adjoin e to the 2x corresponds directly downstairs to this minus 1, 1. Okay. And right, so and 1 corresponds to L itself, and Q adjoin X corresponds here. Okay, so there's some special subcollection of intermediate fields here which survive, which actually do correspond in this lower direct correspondence. Okay. And similarly, there's some special collection of so this is Q-alg, the multiplicative group of Q-alg. There's some special collection of algebraic subgroups which correspond to these under the direct under the indirect correspondence. Okay, is that clear enough as a concept? Okay, so the set of intermediate fields between the set of intermediate fields, which I'll call, which correspond under the lower direct correspondence, I'll denote by F prime, and I'll also call these the derived fields following Epstein, this is Epstein's terminology, derived fields, and the subgroups associated to this, which survive going down in this direction. So 1, -1, and 1, and Q, multiplicative group of Q-alg, in this multiplicative group, I'll denote, so the associated subgroups, I'll denote by this like curly G thing. Okay. So I'll call, yeah. All of them map to something, but okay. So if I take Q adjoin e to the 4x, right, and I take the automorphisms fixing Q, I'm gonna get this group. But I can also go the other direction. I can ask what the fixed field of this. Okay, so what I'm saying. So F prime is going to be the image of this map. Okay, that's what I mean precisely. Thank you. So there are not enough subgroups over here, right? F prime is the set of intermediate fields between L and K, which correspond exactly to the subgroups that do exist downstairs. It's just some of them. It's just some of them. Okay. Okay. It's a subcollection. Okay. Thanks. Okay. As part of the fundamental theorem, I'll also include this Torsor theorem statement, which is just to say, this is a model theoretic statement that, or I'm saying it in model theoretic parlance, that the realizations of the type of the fundamental system chosen is a right K-definable torsor for the Galois group, for this algebraic group G. Okay. All right. So now I'll talk about early existence theorems for Picard-Vessier extensions, one of which we already saw. So for an arbitrary ordinary homogeneous linear differential equation Y over an arbitrary differential field K, does there always exist a Picard-Vessier extension L? So again, one can always find a fundamental system B bar in the differential closure, in which case, when you generate the field L by that fundamental system, the associated extension is a finite algebraic extension. And from this, we get Cauchy's theorem from 48, which is just that if there are no finite algebraic extensions, proper in the differential closure, then if you adjoin any fundamental system, you won't increase the constant. So it'll generate a Picard-Vessier extension. But in general, no. So if you don't have that the constants are algebraically closed, Seidenberg in 1956 constructed a now famous counterexample by building adversarially this field K by adjoining to R a transcendental solution to this equation. So he's kind of getting close to breaking that it's formally real. And then he considers this second order linear ordinary homogeneous differential equation, and he proves that whenever you adjoin a fundamental system, B bar for Y, you're going to increase the constants. You will have to adjoin I. Okay, so what this shows is you can't adjoin a fundamental system without also introducing the imaginary element I, right? So which is a constant. So there's no Picard-Vessier extension for this equation. Okay, so Seidenberg in that paper also analyzes equations of ordinary homogeneous linear differential equations of up to order 2 and gives criteria for when they're going to always have a solution. And he uses an analysis of order 1 equations, which appears in this paper from the year before by the student of Kolchin who produced who gave a related existence theorem. So this is a positive result. So like Kolchin's result, it's sort of a positive result. One can always find a fundamental system B bar such that when you generate L over K by B bar, the constants that you introduce are a Galois extension. And Epstein has 2 papers from that year. The first one is this existence result. The second one is studying these extensions that you get by adjoining a fundamental system which introduces a Galois extension's worth of new constants. So that's what I'll try to describe now is to give a kind of model theoretic account of this. But I'll just describe the statements first. Okay, so the first theorem, which is a slight generalization of Epstein's statement, is the following. So let L over K be generated by a fundamental system B bar for an ordinary homogeneous linear differential equation Y, such that the constants that you introduce are a finite algebraic extension. So this construction works even if the constants CL over CK are not a Galois extension. If you pick the fundamental system from the differential closure, yes. Yeah, which we can do, yeah. In this case, so the theorem is there is a linear algebraic group lying around defined over CK such that the automorphisms of L over K are isomorphic to the CK points of this linear algebraic group. Okay, so now I'll sketch the proof. Okay, are there any other questions before I go on? Okay. So let L be generated as a differential field by B bar over K. So we have an intermediate, so just note that we have an intermediate field, which is L, which is K adjoin CL, the new constants. And L over K adjoin CL is generated by this B bar, so generated by a fundamental system. This is all the new constants are in this extension by constants, so this is a Picard-Vessier extension, so just note that. B bar, by definition, is a CL basis for the solution set. And we have this finite extension, CL over CK. So let D bar, D1 through DM, be a CK basis of CL. Maybe you can see where this is going. Define mu ij to be the products bi dj. This is now a CK basis. This is just linear algebra. This is a CK basis for CL. Okay. What? Yeah, it's a CK basis of the solution set y of CL. So the solution set in L of the original equation that we started with. Okay. Now at this point, right, like Epstein uses the usual differential algebraic approach where he says, let's look at the vanishing ideal of differential polynomials vanishing on this tuple mu ij, but we're going to proceed model theoretically. So look at this type. Is this okay? Jim, it's okay? Okay. Now mu, okay, so type of mu over k is isolated by a formula. Okay, so if we pick the fundamental system from the differential closure, this is like immediate, but it'll be true in general. And one shows that, okay, so, right, okay, so this is the definition of the group itself, G. Okay, so what I'm saying is if we take an automorphism, L over K, apply it to mu bar, you're going to get another basis for this differential field, for the vector space of solutions of this differential field. And you're looking at the matrix of constants, which will be in GLNM. Such that multiplying on the right by that matrix of solutions takes you from one realization of the type of mu bar to another realization of the type of mu bar. Okay, one has to check that this actually works, but this is how we attach a group G living on GLMN to this kind of equation. Yeah. Yeah. So there you work exactly the same way, except you don't. So again, you look at the type of B bar over K. It's isolated. You find a formula which isolates the type of B bar, and then you look at realizations of that type. Wait, so one. Okay. Yeah.
Regardless of the construction, right?
Yeah.
Existence of this G isn't already given Cauchy's theorem, because it didn't depend whether the constant were algebraic goes or not, right? The one you stated at the beginning, right?
Okay, yes, but actually okay, what's used there is that it's a no new constants extension. This is not a no new constants extension. That's the major difference. In both cases, I'm not assuming algebraic closure of the constants, but here I'm allowing CL/CK to be non-trivial. Yeah, Ronnie? In theorem 1 of Epstein, the CL over CK is assumed to be a Galois extension, but in fact, this construction works just okay. Now, yeah, and his description of the correspondence will rely on this, the fact that CL over CK is Galois. So we'll reintroduce that later. Okay, can I proceed? Okay, so let me just revisit. Okay, so basically, right, CL over CK, L over K joint CL is a Picard-Vestio extension. So in any one of these extensions, there is a PV part. And to understand the correspondence in this setting, we'll now look back at the PV part, which again is kind of contained in this picture, and just refine it slightly. So this is a statement. So to state, yeah. So we're going to sharpen slightly the understanding of the lower direct correspondence. So as I said before, looking back at this picture, the set of fixed fields under this lower direct correspondence, we're going to denote F prime. The set of fixed subgroups, we denote G prime. So this proposition is kind of adapted from Epstein's paper, but it doesn't actually appear as like written in almost anything like this in his paper, but it's very much influenced. Like it's kind of just an adaptation of some of the results there. Okay, and it's about it's a statement about Picard-Vestio extensions. So let L over K be a Picard-Vestio extension. And it's a characterization of this F and G. Okay, so the characterization is exactly the last line of this proposition, that an intermediate differential field L1 is in F prime, it's fixed under the lower direct Galois correspondence, if and only if the associated group under the indirect Galois correspondence is Zariski, its CK points are Zariski dense in the CK diff points. Okay, in which case that group survives. Okay, so what the entire content of what I'm saying is that the arrows that go here and here are, you take CK points, and here you take the Zariski closure with respect to CK diff, which is an algebraically closed field. Okay, so how does this play out in the example? Okay, what I'm saying exactly is one of these groups is going to be circled. So for example, this is not circled because when I take the CK points, I get this, I get -1, 1. And when I take its Zariski closure, again, the Zariski closure of -1, 1, -1, 1 is just going to be -1, 1. So it's not equal to its Zariski closure when you go down and up. Okay, so that's the whole content of this proposition. Is that okay? Okay, so we're just refining slightly this. This is a statement about Picard-Vessio extensions. Maybe it's known, maybe it's known, but or it's I guess it's implicit in Epstein's work, is sort of what I'm saying. But I haven't seen it anywhere, so I wrote it down. Okay. Partial correspondence with new constants. Okay. All right, so now I will describe the statement of the correspondence in this setting of Epstein. Okay, so let L over K be generated by a fundamental system, B bar. For what I'm about to say, we're going to still be in this case where CL over CK is a finite algebraic extension, but in the actual statement of the correspondence, we'll assume that CL over CK is a Galois extension. So let L be, so again, L is generated by K join B. We have an intermediate field K join CL of the new constants adjoined. Let H be the CL definable Galois group associated to the Picard-Vessio part of this extension. Is that okay? So L over K adjoined CL is PV, and the constants of that extension are CL. So the Galois group will be a CL definable algebraic group. Let G be the group which is constructed via this mu thing. Okay, there's a map. So the automorphisms of L over K joined CL include into the full set of automorphisms of L over K, the full group of automorphisms. And so we have a map phi, capital Phi, from H join, so that from the CL points of the Galois group of the PV part into the full thing, and I'm going to call the image GPVCK. So this is the statement of the correspondence. Okay, so let me maybe I'll try to write it more nicely. So now for the correspondence in this setting, we have to assume that CL over CK is Galois for this to be true. Okay, I'm going to, and the statement is that it's a partial Galois correspondence. So not every intermediate field is going to correspond to every subgroup of GCK. Okay, so and what subgroups am I talking? What is the full set of possible subgroups of GCK? It's the CK points of all algebraic subgroups of G. Okay, so I'm defining the okay, yeah, so maybe can I erase this? Is Oh, actually, I have another board here. Okay. So, okay. So, yeah. So to be very precise, so definition. F is a collection of differential fields of intermediate differential fields between L and K, which I'll call the fixed fields. Okay. So what's the characterization, or this is a definition. F is in this curly F if F prime, the smallest derived field. So F prime is in F, the previous F, curly F prime. And again, this is with respect to the PV extension L over K adjoined CL here. So that's the sense in which I mean this capital F prime. So if F prime, the smallest derived field, satisfies, if F and F prime together satisfy two conditions, one is that F prime over F has to be Galois. Oh, thank you. Thank you. Yeah, sorry. Yep, exactly. Containing F. Yeah. Okay. Yeah. Two. Thank you. Every automorphism of F prime fixing F lifts to L. Okay. So that's one set. Now I'll define G. So G, the definition, G is a collection of intermediate subgroups between the identity and G of CK, where this is the group living on GLN. This is inside of GLMN CK, right? Again, this is the one that we constructed by this mu thing. So it's a collection of intermediate subgroups called the fixed subgroups, called fixed subgroups. And G1 CK is in curly G if phi inverse of G1 CK intersect this GPV CK is in curly G prime. Okay, and again, where curly G prime is with respect to the extension, with respect to the PV part, right? With respect to L over K adjoin CL. Okay, so the statement is that these fixed, this is a definition of a collection of intermediate subgroups. Okay, and really the statement of this theorem is that those are exactly the ones which correspond via stabilizers and fixed field. So I've defined okay, F is a collection of intermediate fields between L and K, and G is a collection of subgroups of this Epstein group defined by this property. No. The theorem is separate. These are two definitions, and the statement of the theorem is that F and G correspond. So actually, Yeah, so I should have said, no, you're totally right. I need to say that F and G correspond. So the fixed fields correspond. That's the,
So what's the definition of F being fixed?
that's this definition. Yeah, so the statement of the theorem is that there's a correspondence between the elements of curly F and curly G. No, but I'm saying this theorem describes the partial correspondence, and I'm telling you what the fixed fields and the fixed subgroups are. So it's sort of implicit. But okay, sorry, I should be explicit. You are totally right. Is it okay? It's okay. Oh, I have the chalk and I put the thing over there. Okay, okay, the statements up to now have been hopefully differential algebraic enough. Maybe not the proofs, but the statements at least. But now I will describe very, very quickly the model, an approach to giving a description of this construction of this group G via these mu ij's, but in terms of the binding groupoid machinery, which is coming from internality. Okay, so I'll say it. I'm gonna say this part very quickly. What should I say? Okay, maybe I'll just start. Okay. So yeah, the point of what I'm trying to do now in this part of the talk is just to give a more generalizable description, right? A priori, the construction of the group G looked like it depended a ton on the linearity of the original equation, and it was via this via linear algebra. But so this is a model theoretic approach that will hopefully free us from that a little bit. So okay, so the setup is now we're working with reference to a bigger model than the differential closure monster model. K is a differential field. Y and X are K definable sets. Again, Y in your head you should have as being a linear differential equation roughly, and X as being the constants, as the equation defining the constants. So we say that we saw this definition. We saw a definition for types of it related to internality in Christine's talk, but I will talk about definable sets as being internal. So we say Y is internal to X if the realizations of Y in the big model are contained in the differential field generated by K, the realizations of X, and B for some small set of parameters. By compactness and a standard coding trick, there's a K definable function and a tuple B bar from this parameter set capital B, such that essentially this tuple B bar is like a basis for the solution set of Y. It's parametrizing Y in terms of elements of X. And the statement is that this is surjective. By definability of types in DCF0, we can replace B bar with a tuple of elements Y. I should say that this construction is very standard, and so I'm just kind of going through it. So by definability of types in DCF0, we can replace B bar with a tuple of elements from Y to the N, actually, which we call a fundamental system for Y. The set of such fundamental systems is K definable, and following some replacements in notation, we can assume that that there's this set X1 living on a quotient of the original Xn sort, so that this is a bijection, not just a surjection. So in your head, so I'll give the analogous statements in the case that we have the linear differential equation in the next slide or two. But we can define a definable groupoid action living on Z and X1 as follows. So for any fundamental system, if you look at its type over the base field K and X, which you think of as the constants, this type is isolated and will be definable over a finite tuple of parameters D bar from X, which you should think of as the new constants adjoined when you generate a field by B. Let Q D bar be the set of realizations of this type. Then there is a K adjoined D bar definable group acting on the right freely and transitively on the set of realizations. And it's defined as follows. So if I have any two distinct types of fundamental systems over Kx with associated tuples D1, D2, we define H D1, D2 in exactly this way. It's the set of elements in this set X1. So you should think of this as being like GLN, which take you via this function f from one realization of type 1 to a realization of the second type. Okay, and the notation H sub D bar is really shorthand for H sub D bar, where the D bar is the same. Okay, additionally, there's another model theoretic incarnation of the Galois group, which acts on the left, which gives each of these triples the structure of a definable bi-principal homogeneous space. Okay, but okay, and now I'll say precisely the relationship to the PV theory. So elements from fundamental systems of a given type generate generalized strongly normal extensions, which are generalization of Picard-Vessier extensions, exactly when this tuple D bar lives in K. And this corresponds to weak orthogonality of the type of B bar over K to the set X. In this case, both H plus and both incarnations of the Galois group are K definable, and are K definable. And okay. And we define a definable Galois extension, or generalized strongly normal extension DCF0 to be an extension L generated in this way. Okay. Epstein's group in terms of the binding groupoid. Okay, so now I will give a description of Epstein's group in terms of the binding groupoid. And ordinary homogeneous. So again, so now we're doing the construction of the previous two slides starting with our internality being of the following form. Y is internal to the constants. In this case, the set of fundamental systems, which is this set of bases for this vector space of solutions, is a right PHS for all of GLN CK diff. However, those fundamental systems may comprise different types. May comprise different types. They may be in different types over K adjoin over K and even over K adjoin X. Okay, so let L be generated by some fundamental system such that the new constants adjoined are Galois over K. We can find this by Epstein's first result. Let capital lambda be the set of Galois conjugates of D bar, and let H0 be just a finite representation in K of this finite Galois group. Okay, so this is the description of Epstein's group. This is a description of Epstein's group in terms of this Galois groupoid. Okay, so as I've written it, it's a CL. This is the description I'm giving here is of on the right-hand side, we actually have a CL definable group, and on the left-hand side, we have a CK definable group. But okay, so maybe I won't explain it too much, but the point is somehow that if you take an automorphism of the big model, you apply it to the fundamental system, this is going to also move the constants, the new constants that are adjoined. And okay, and you look at the orbit of the new constants, because you assume that the new constants are a Galois extension, the orbit of the constants isn't too big, and it also can be kind of controlled by this definable group H0, and you paste together the parts of the groupoid living above that orbit. Okay. There are I give a bunch of different incarnations of this thing on the right-hand side in the thesis. Okay. I'm a little bit over time, but I'm just going to state this quickly. Relationship to Umemura's quasi-automorphic extension. So Umemura has a definition of quasi-automorphic, of a different flavor of differential Galois extension, which he calls a quasi-automorphic extension, from a paper of 1996 called, okay, which we'll see on the references page, the title. A differential, finitely generated differential extension, L over K, inside of KDiff is called quasi-automorphic if it is generated by a point on a definable PHS for an algebraic group defined over CK. That is, okay, this is my, like, you know, kind of model theoretic rephrasing of the definition that appears there. So much work, you know, there's work remaining to check that those things match up. This is my interpretation of his definition. Proposition, okay. L over K is quasi-automorphic, and so this is actually a proposition that appears in Umemura's work. Okay, so this is not my take or anything like this. The first line is Umemura's is from directly Umemura's paper. L over K is quasi-automorphic and is a no new constants extension if and only if it's actually a strongly normal extension in the sense of Colchin. Okay. He has a section in the paper titled "Relationship to the Colchin Theory," and this is exactly his criterion that he gives. So if you have a quasi-automorphic extension and it's a no new constants extension, then it's actually strongly normal. And it's easy to observe, although not explicitly stated there, that if the group G, which he calls the group of automorphy, is linear, then these should correspond exactly with the Picard-Vessio extensions. Okay, so I'm claiming that, like, or I'm saying that it's easy to see this. I'm not claiming it, but I'm claiming that the only thing I'm claiming is that it's easy to observe it. That although it's not stated in his paper, one can characterize the PV extensions L over K as exactly the linear quasi-automorphic extensions with no new constants. This is, what do you mean? What do you mean by Colchin? Yeah, right, exactly. But yes, exactly. That's the argument. Yeah, easy to observe. It's Colchin's thing. So this is now something I'm positing, that L over K is linear quasi-automorphic with CL over CK Galois exactly when L over K is an extension from studied by Epstein. Okay, so and I guess I'm positing even more in general, which is that L over K is linear quasi-automorphic if and only if it's an extension generated by a fundamental system to an ordinary homogeneous linear differential equation. I'm positing it. I'm not conjecturing it. Softer than a conjecture. Softer than a conjecture. That's what I'm trying to say. Remains for future work, but okay. Final remarks. The model that XG of a quasi-automorphic extension is not uniquely determined. So if you have a quasi-automorphic extension L over K given in that definition, the group G and the PHS is not uniquely determined. Okay. 1. 2. Umemura has a stronger definition of an automorphic extension, and I don't have any kind of conjectural, even model theoretic definition of that type of extension. I think that is something that I want to think about, and and I think it, yeah. So I'm having trouble reading it even and figuring out what exactly is going on there. But it's as far as I can tell, it's intended to kind of generalize or it's related to a notion of Hop Galois extension, which I also don't have a handle on really. And also, lastly, I just want to mention that Umemura has a parametrized version of his quasi-automorphic extensions. Okay, thank you very much. Very, very